Okay. Let's share it back again. So we are now on the third order, trimolecular. Some textbook will call it thermolecular type of reaction. Under this particular type of reaction, we also have three cases. Okay, so case one is the case wherein you have three different species on the left side of your reaction, and if it's elementary, this is elementary, the rate law or the rate equation would look like this. So it would be rate law if you have negative R sub A here equated to K, C sub A, C sub B, and C sub D. It would be rate equation if you have that derivative here equated to the right side. Okay? Now, if this particular derivative is written in terms of conversion, so it was shown to you already last meeting, it would look something like this. And if this particular right side here is represented in terms of conversion on A only, so you have to find a representation or an equivalent expression for the concentration of B at any time in terms of the conversion of A. Now, why will you do that? It's because your DE here, or rather your derivative in here in your DE, has the unknown function as the x sub A. So you should convert the expression here on the right side, which are all concentrations, in terms of the conversion of A. That way your DE can be processed. If not, then there's no point of having to write the left side in terms of conversion if the right side is in terms of concentration. You just have to simply make the left side and the right side of your equation mathematically homogeneous. So in terms of unknown function, it should only be 1. In terms of the independent variable, it should only be 1. So that's the reason why you have this. Now, it was also shown to you last meeting that you can express initial concentrations of your species as ratio. So we have this represented as M, and this one is the ratio of D with respect to A, initial concentration, that is. Now, the reason why you have CaO here raised to 3 already, it's because you have already multiplied the original right side, this original right side, by CaO over CaO. How many times do you have that square? Because you have 2 CaOs here used as a divisor, so meaning you have multiplied the right side here by CaO over CaO quantity squared. That way you will have these initial concentration ratios, and you will have conversions here in terms of XA. And how you express, let's say for example, CBOXB to CAOXA, it was already discussed last meeting. You go back to the stoichiometric ratios. That is the amount of B reacted over its coefficient in the stoichiometric equation is equated to the amount of A reacted over its stoichiometric coefficient, the same thing with D. So that you will have the amounts of the other species related only to A. That way you can single out, or you can, shall I say, represent the second term in here solely as a function of XA. So that was already discussed, and I won't anymore go back to that. Okay, so this will be your DE. You have a DE. If you do separation of variables, you will have to use the method of partial fractions, because you have here 1, 2, 3. 3 linear factors if we're going to look at it in terms of the variable or in terms of the unknown function x sub A. If you will process this DE, this is the finished equation derived already by Levenspiel. So this is the equation given in Levenspiel. So you have 3 rational expressions here that are being added, because if you process the original DE here using the method of partial fractions, you also have 3 partial fractions. So that is why you have 3 terms here on the left side. And you have here simply a KDT on the right side, which will yield a KT. Now, this is your formula for case 1 under thermolecular or trimolecular third order type of reaction. Now, there's a note in here, and this is specifically stated as well, that when the initial concentration of D is much larger than both the initial concentration of A and B, the reaction becomes second order. It's exactly the same principle as discussed also last meeting when one particular reactant in terms of concentration initial concentration rather, is higher compared to another. That's in the case of the second order type of reaction. If one concentration is too large compared to another, it's like if you're going to monitor how its value or how its concentration behaves over time, the changes in the concentration of that particular component that is present in let's say a very big amount compared to another will be very negligible compared to the change in another. Just like saying that the concentration of that particular species present in the largest initial concentration is unaffected compared to the other one. So it's a pseudo first order type of reaction, though it is second order. So it's the same thing as this. So if this D species is much larger in concentration as A and B, it's like as the reaction proceeds, we will notice that the concentration of D is unaffected, whereas the concentrations of A and B already displays a much higher change from its initial concentration. So just saying that the rate of reaction is not anymore dependent on the concentration of D, which is present initially in higher concentration compared to the two, or a much higher concentration compared to the two species A and B. So that's the explanation here wherein your reaction, instead of being third order, it's a pseudo second order reaction. Okay, kung sa aton language daw, second order na lang siya. Ay hindi na ang concentration ng D a factor to consider in the rate of the reaction of the system, having A, B, and D. So this is our case 1. Now our case 2 is something like this, and this is the most common type for a third order thermolecular type of reaction. You have here another elementary reaction because it's first order with respect to A and second order with respect to B. Okay? If you're going to again express our C sub A in terms of conversion and use again the initial concentration of the species, the ratio of such, then you will have a different equation here in terms of conversion. So you can see these are all now XA. M is still defined as CBO over CAO. Now, this would still be again processed using the method of partial fractions after separation of variables in DE. And your formula or your working equation would be this. If the initial concentrations of B and A will not be equal to 2. So this is your formula if CBO and CAO, or CBO divided by CAO, is not equal to 2. If it's equal to 2, you will have this simplified equation to use. So this is the product of, or this is the resulting equation if you evaluate your DE using separation of variables and the method of partial fraction for integration. I'm referring to this one. Okay, so this is for case 2 under third order irreversible reaction. Now, the last case is similar to case 3 under second order bimolecular type of reaction. And it's like this. So looking at it, it's never elementary because you only have 2 species here with 1 mole for each. If this would have been elementary, this should be K C sub A times C sub B only. But we could see that based on the rate law, your reaction is first order with respect to A, second order with respect to B, and third order overall. So does not agree. It does not agree with our stoichiometric equation. So then, this is a non-elementary third order type of irreversible reaction. Now, if we will have here concentrations as is, we will not express it in terms of conversion. I'm saying that because your resulting equation here does not have any XA, it's not in terms of conversion, meaning this was treated, your DE here was treated as is in terms of concentration. So you just have to express CB in terms of CBO and CBOXB, also converting CBOXB in terms of CaOXA, using again stoichiometric ratios from your provided equation. Now, if you do that, this is your formula, class, if the ratio of CBO to CaO is not equal to 1, meaning initial concentrations of A and B are not equal. If they are equal, this will be your simplified working equation. For case 3, third order type of irreversible reaction. Again, you can use this set of formulas, the 3 sets of formulas, whenever applicable to a given scenario that is being described by the problem. Okay? So far, do you have any questions for third order? So we have 3 cases. So case 1, it's elementary, having 3 different species. Case 2, it's still elementary, having 2 species. And case 3, which is non-elementary. So this is for the third order type of irreversible reaction. We're done with the first order and the second order. Now, since we have that, then we might as well discuss the zero order reactions. So these are reactions wherein you can't see any concentration dependent term on it. So you don't have any concentration term in here. You only have the rate constant. It's because for the zero order type of reaction, the rate is not dependent on any concentration or on the concentration of the reactant present. So it's simply written as this one. This is very, very easy to evaluate because you simply have to separate variables and directly integrate the resulting expression or equation. Separate the left side and the right side. If you do that, this will be your working equation. Okay, you can stick to the original DE and you will have CaO minus Ca equated to Kt. Now, if this CaO is subtracted with Ca, where CaO is the initial concentration and Ca is the final concentration, or the concentration of A after some time, if you take the difference of these two, it represents the amount of A that has reacted. Initial minus final is the amount that has reacted or the amount that has disappeared. So this is your working equation. Now, however, you have to be very, very careful in the case of zero order reactions, class, because there's a need for you to test first the given information by the problem, because it's possible that given the time in which you are to determine the concentration of your species, you may wonder why your answer is negative. It's because for this type of reaction, it will come to a point that there will be no reactant present, and if computed from the equation here provided, this one, you will wonder why the concentration will be negative already. Meaning, if it's negative, there's none of A left already. So you have to test first, class, if the time which is given in the problem wherein you are to determine the concentration is less than CaO, the initial concentration that is given, and the rate constant. So you first solve this one, the CaO over K, and compare it with the time in which the problem is asking you to determine the Ca. If that particular time, if the time that is given or stated in the problem is less than the computed CaO divided by K, this should be the formula that you will use. If the time that is given in the problem for you to determine the C sub A is greater than or equal to the CaO over K, which you have computed, automatically class you answer for the concentration of A left to be 0. Why? Because if you still use this particular formula, your answer will be negative. So you use a different formula for these two scenarios for zero order reactions. If your concentration as computed is negative, it means class that there's none left already. But nonetheless, for it to be safe, first solve the initial concentration divided by the rate constant and compare it with the time that is given in the problem to determine the CA. That way, you will not have a problem or you'll be confused why your concentration as computed is negative. Okay, so this is for the zero order reaction. And these are very important things that you should know about zero order reactions. So for zero order reactions, conversion is proportional to time. So meaning, as time elapsed at the start of the reaction is increased, conversion is also increased. So over time, we could see that as time proceeds, conversion is increasing until it reaches 100 or 1.0. Now, as a rule, reactions are zero order at higher concentration ranges. At very high concentration ranges, it becomes zero order because this time the rate of reaction is not dependent on the concentration of that particular species. Why? Because its concentration is very high. So meaning after some time, there is not much change on the value of the concentration of that thing that is being converted or used up in the formation of the product. Okay, so it's zero order at very high concentration. Now, zero order reactions then are those reactions whose rates are determined by other factors other than concentration. So you can see there's no concentration term on the right side. So then, what would be the factors then that will affect the rate of a zero order reaction? So these are the other factors that will play a role in the speed of the reaction. And these factors are the following. So intensity of radiation within the vat. So if it's going to be a first order reaction wherein there is some form of radiation that is happening in your reactor, then the intensity of that radiation will be a factor affecting the rate of reaction. In the case of photochemical reaction, that would be the case. Okay. Now, in the case of reactions wherein you have solids, you have catalysts, so the surface available in certain solid catalyzed gas reactions. So the rate of reaction then will be dependent on this available surface of the solids acting as a catalyst for the solid systems. Okay, so that's in the case of the zero order reaction. Now, in this scenario from 0, 1, 2, 3, or 0, first order, second order, and third order reaction, you may guess and then you may test whether your guesswork is correct. Now, in the next part here of the slides, you are given the option to directly come up with the general formula to use in determining the order of the reaction and the rate constant. Okay, now that particular formula is shown in here. It's general in the sense that N is written as N, since you do not know what that N is, and K is also written as K. These two are unknowns. So a generic way of writing the rate equation or the rate law. If you will process the dE, the second and the last terms here, you equate, this will be your expression. You have N as the unknowns, and you have N and K as the unknowns. So given, let's say for example, the concentration and T data, or the time and the corresponding concentration of A left after that particular time has elapsed for your reaction, you can go back to this equation and determine the corresponding value of N and K. So the question is, how will you do that? So this is how you're going to do it. So from this particular formula that you have, you rearrange from here, you rearrange that way, you will have CA raised to 1 minus N minus CAO raised to 1 minus N. You isolate the K class in this side, so you divide by the quantity N minus 1 here over time. And this is the K. This is what I suggest to my students. The problem will give you most of the time concentration and time pair of data. So you have this data here for concentration and time. So they are paired. Of course, together with the initial concentration of A. So that should be given. What you do, you substitute it here. So you pick one pair and substitute the CA and the T in here. And of course, the CAO, which is a constant. Now, this equation will give you two unknowns, the N that you have in here and the K. Now, this K that you have will remain constant for all pairs of CA and time values that you will use. So, the reason why it's mentioned here, it's trial and error. The CA and T value pair that you will substitute in here should come up with the same K value if we speak of the same reaction. So meaning I use this pair or this pair, or this pair of data, I should be coming up with the same K value. So what I suggest to my students, since it's trial and error, you first assign a value for N here. And by the way, you cannot assign a value which is equal to 1. Why? Because this will all be raised to 0. And that would be 1. You can assign any value for N here together with the CA and T value and the CAO. And so for the K. For whichever N value that you have substituted here, where K will not vary that much. For example, for the first pair, your K is 0.0012. Example. For an assumed N, let's say you assumed N to be 1.2. So for the next pair of data, you still assume this 1.2. And you use the second pair of data and so for K. So for example, for your next K, you have 0.00119. You're okay. Then next, the same thing. You use this pair of data, the same N that you assumed, and you will have, let's say for example, K is 0.0118. So more or less, you can say, based on the trending here, that your N, the assumed N value, will give you more or less the same value for K. Because they are all of the same range. If that is the case, your assumed value of N, which is 1.2, is acceptable. Because your K does not change that much. Does not change, so meaning this N is acceptable. That's the reason why it is said to be trial and error. However, the beauty of this particular process is you don't have to guess and test several equations. In here, you're just dealing with one particular equation in which you will substitute the value which you assumed initially for N. Now, let's say, for example, you have this for 1.2.0012. Let's say you have that. But here, let's say for the next K, or the same order, let's say your answer is 0.0023. Right away, class, don't stick to this anymore. You see already this big difference. So meaning this, it's not really 1.2. You have to think of another one. Let's say 1.4, 1.5. You may think that it's just like looking for the needle in the haystack. No, I've done this several times already. You just don't assume very big values initially and increment it in small numbers. Don't increment like from starting with N equal to 1, you will increment right away to 2. You don't do that. Unless otherwise you see that there's already there's a big difference in the computed K. But at some point, you will even get the actual value of the N wherein the K does not change anymore. So what I'm telling you in here is if you have this particular given set of empirical data, you should add another row here. It could be above or below, and so for the K here. The case here for all this pair of data for the same assumed value of n should be more or less the same. If they should be vary, probably not as big as this one. Okay? So this is how you use the empirical rate equation of nth order in determining the order of the reaction, or specifically both the order and the rate constant of a pair of a set of empirical data. Now, what I like about this empirical rate equation of nth order also is that you are not limited to integral values of the order. So if you can recall, when you assume for zero order, first order, second order, third order, they are all whole numbers. They are integral values. 1, 2, 3, 4, 5 integers, only that they are not negative. In here, we don't limit it to whole numbers. You can even assign an n value which is negative and not at the same time a decimal. Whereas if you do the guessing and the testing, you'll be limited only to 1, 2, 3 or 0. Whole numbers sila tanan. Am I getting my point? So most of the time, my students, when given an empirical data to test and it's integral analysis that they will use, they resort to using this empirical rate equation rather than really guessing a particular rate expression and testing the fit of the data to that particular guessed rate equation. Now, do you have any questions so far to what I have covered in here? So did you all understand what has been discussed? Okay, so I will clear my screen if there aren't any questions anymore. Now, there are, however, very important generalization to this empirical rate equation of nth order. And this is very important, class. Okay, I'd like to discuss this one. Now, for reactions, I'm referring to this, the generalization based on this particular equation. Now, for reactions with order greater than 100% completion is not attained in finite time. What do we mean by this? For reactions with n greater than 100% completion is not attained in finite time. Can you tell me of your understanding of this particular concept in here? You can write on the chat box. What's your understanding of that? Or you can use your microphones if you have your microphone there. What do you think, third year? For n greater than 100% completion is not attained in finite time. What do you mean by that? Ma-indefinitely siya is kay ma-zero ang denominator. Other answers? For this particular type of equation, I hope you could see my slide. If n is greater than 1, it says here 100% completion is not attained in finite time. How do you understand that? When we speak of 100% completion, what do you mean by that? What's your understanding? Hmm? Fritz, how do you understand 100% completion? Is Fritz here? What do we mean by 100% completion? Or what about Jelaine? What do we mean with 100% completion? You can write on the chat box. Jelaine, are you there? Sige. I will remove participants in the room if you don't say anything there, because how will this class be then a class wherein there is exchange of ideas? I don't want this to be a monologue in 1 hour time. What about Jericho? What do you mean with 100% completion?
For me, Miss, I think all of the reactants have reacted.
Again.
Ang tanan na reactant, naubos na Miss ang reactants.
Very good. Samo na siya, tsakto na siya. When you speak of 100% completion, so meaning your reactants have all been consumed in the formation of the product. So now Jericho gave you an idea. 100% completion will not be attained in finite time using this particular formula if n is greater than 1. How do you then finish off what Jericho started? John Albert Villarosa. If it says 100% completion is not attained in finite time, what's your understanding of that, John?
Hindi siya complete, Miss. Adik ang may mga what do you minus
100% completion, amo na itong hamba ni Jericho. Na 100% completion meaning your reactants are all consumed in the formation of the product. Or if we're going to use another term there, conversion. I'll use conversion. 100% conversion will not be attained in finite time. So what do we mean by will not be attained in finite time?
Tekang iban.
Ay, sige, Jad.
Di lang ko sure, Miss. Tekang iban, daw why na form as product, so hindi siya kompleto or like hindi siya pwede bala misaw.
Hindi pwede matabo nga.
Like hindi complete ang product, like daw it's dapat
your product will always be complete. Your product will always be complete regardless whether your reactants were all consumed or not. Your product will be your product. Doesn't mean na kung ma-form kita, for example lang ma-form kita sodium hydroxide, hindi na siya mag-sodium hydroxide unless naurotan na niya reactant. It would still be formed as sodium hydroxide. Only that, not all your reactants were converted because of this phrase, 100% completion is not attained in finite time. Okay? What is this phrase? What do you understand this phrase? Will not be attained in finite time. What's your understanding of that?
May limit, Miss. Kung finite time.
Pag sinin ka finite, what do you mean by finite?
May limit, Miss.
May limit, meaning ma-solve, right? Ma-determine mo gid. Ma-solve siya, ma-determine mo gid. Amo na siya namin. Kaya magsinta finite, may limit. So if you're going to rephrase this particular concept in here using the empirical rate equation in the determination of n and the k, for n, for a computed n value of greater than 1 plus, it is impossible for you to be able to solve or determine that specific time when xa is equal to 1. This is what it meant by this. For orders which is greater than 1, like 1.2, 5, 3, 3.5, they are all greater than 1. If the problem asks you to determine when will the conversion be 100%, you cannot answer that even if it's just a simple question of true or false. Why? Because of this thing here. You cannot determine that definite finite time when reaction will be 100% completed. We say reaction is 100% completed when all your reactants, as what Jericho was saying a while ago, has been converted to the product or products. Okay? So that's for n greater than 1. What about for n less than 1? So for reactions with n less than 1, meaning 0.9, negative 0.2, 0.6, so they are all less than 1. Reactant concentration will fall to 0. It will fall to 0, meaning there will come a time that your Ca will be equal to 0. And even then become negative at some finite time. So if you're going to use the empirical rate equation, it is even possible for orders of reaction less than 1 that the Ca value that you will be solving is negative. Just like the way I have explained it with zero order reactions a while ago. It's possible that using the equation, you'll have a concentration which is negative because of this. That is for order less than 1. So it's possible that you can have negative concentration. If you solve for a negative concentration, don't answer that particular negative concentration. Why? Because we don't have such thing as a negative concentration. So meaning at that particular time, all your reactant A has been fully consumed already. I'm referring to this order of less than 1. So it says here that for T, which is equal to greater or greater than this value, automatically the concentration of A will be equal to 0. So if you would be asked to determine the concentration of A at time equal to 90 minutes, before you do that, first check the time in which this CaO raised to 1 minus n, your n being less than 1, over 1 minus n over quantity 1 minus n times k would be. What is this time? Again, compare it with the time which the problem is asking you to solve for the concentration of A. If your computed time, or rather if the time that is specified is greater than this, automatically you answer Ca equal to 0. If you don't and you use the original empirical rate equation, you will be able to solve a negative concentration. So, hindi man na siya acceptable kung negative at concentration. So, that's the reason why you need to check first whether this value that you have is, or the time that you have is less than this value. So, determine this first. That way, you will have a basis or I think to compare the time in which the problem is asking for the concentration of A. That is if you are using the empirical rate equation. And that is for this condition, that n is less than 1. For this one, it's n greater than 1. I always remind my students about this too because it's very important. It has an implication in the manner you answer questions related to problems that you will encounter later on. If it's a simple true or false, you have to know why it's true and why it's false. Or why is it possible or why is it impossible without having to really go down to the derivation why it's impossible and why it's possible. It's because of this. Okay? So more on this generalization, in real systems, the observed fractional order shifts upward to unity as reactant is depleted. So I'd like to end here. What's your understanding of this? In real systems, systems that you encounter in the industry, the observed fractional order, fraction, order, shifts upward to unity as reactant is depleted. What do we mean by this? What's your understanding of that? Drexel.
Yes, miss.
Do you have, what's your understanding of this?
Miss, as reactant is being consumed, miss,
Mm-hmm.
palapit siya, miss, sa 1 ang fractional order, miss.
Meaning the n, which is fraction, will what?
Will, ano, miss, tawag na, will approach 1, miss.
Okay. So, sakto na siya. Example. So it would have been explained better if you gave an example. For example, your order of reaction is 1/3. Fractional order, it says here. Fractional order. This 1/3 is less than 1, right? Less than 1 siya. So for real systems, the observed fractional order, let's say for example, 1/3, shifts upward to unity. So meaning this approaches 1. When? What is the condition that brings about this one? When your reactant is about to be depleted. When your reactant is about to be depleted, this is a condition wherein your Ca is more or less 0. It's about to be depleted, so meaning nothing left, or when your Xa is more or less equal to 1. Okay? So for reactions in which the order is less than 1, fractional in nature, decimal. This could even be n equal to 0.33. That's still fractional order. As your reactant is being consumed in the formation of more products, as it's nearing depletion, or as the reaction is nearing completion, meaning 100% completed, this order changes. It's not fixed at n equal to 0.33. You have to remember the class that the n and the k of a particular reaction should not change when we speak of that particular reaction. It should not change over time. The K and the order of the reaction should not change over time. So as a consequence of the empirical rate equation, it means that if you use that particular equation, you will notice that as your reactant gets to be used up, or as the reaction gets to be 100% completed, in the cases of reactions in which the order is decimal or fraction, that order changes. It does not stay there at 0.33 or 0.5 or 0.75. As C sub A becomes 0 or approaches 0, or X sub A approaches 1, that particular order of the reaction shifts. So the term is shifts upward to unity, meaning it approaches a value of 1. So this one approaches a value of 1. This is only true for these cases. And that's for real systems. Okay? Now, do you have any questions so far as to the things that we have discussed today? Any questions?
None, miss.
So you will have time later this afternoon for your problem set, because you have to derive those equations, and I think the next problem set can still be solved when I have reached that portion already. Okay, I will stop sharing for now.